Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. So we are from group 4. Today we'd like to present the electronic materials slide number 15 until 20. So firstly, I would like to introduce ourselves. So my name is Muhammad Safwan bin ANUARI and my matrix number is 192074.
Okay, hello. My name is Muhammad AMIR MUSTAQIM bin NAZAR and my matric number is 193249.
Okay, so for the first slide, for the first subtopic of this chapter is which is the intrinsic semiconductor from our part. Okay, what is the intrinsic semiconductor? So intrinsic semiconductors can be categorized by the electron band structure. So it's shown in the figure D, which is empty conduction band, band gap, and low valence band. So the intrinsic semiconductor is a completely filled valence band. It's so separated from an empty conduction band by a relatively narrow forbidden gap, which is generally less than 2 eV. So for the intrinsic semiconductor, it can be categorized into two types, which is the elemental semiconductor and compound semiconductor. So for the elemental semiconductor, it is a pure material semiconductor called as a pure material semiconductor, such as silicon and germanium. So these material have a band gap energies approximately 1.1 and 0.7 eV. So this group can be found in group IVA in a periodic table and are covalently bonded. In addition, there is a compound semiconductor. So compound semiconductor material also display intrinsic behavior. Okay, one such group is formed between elements of group 3A and VA, which is called as 3V compound. So the example of this group material is gallium arsenide and also indium antimonites. And secondly, is the groups 2V and VIA. So it's also called as 2VI compound. So the example of materials of this group is cadmium sulfide and zinc chloride. So as the two elements forming these compounds become widely separated with respect to their relative position in the periodic table, so the electronegativities become dissimilar. So the atomic bonding becomes more ionic and the magnitude of the band gap energy increases. So it can be concluded that the materials tend to become more insulative. So there is a intrinsic semiconductor. Every electron excited into the conduction band, there is left behind a missing electron in one of the covalent bonds, or in the band scheme, a vacant electron state in the valence band. So under the influence of an electric field, the position of the missing electron within the crystalline lattice may be thought of as moving by the motion of other valence electron that rapidly fill in the incomplete bond. So this process is expedited by treating a missing electron from the valence bond as positively charged particle, is called as hole. So a hole is considered to have a charge that is of the same magnitude as that for an electron but opposite sign, which is 1.6 times 10 power of negative 19. Thus, in the presence of an electric field, excited electron and holes are moved in opposite direction. It can be seen when the in the second figure, which is the applied electric field, which is you can see one arrow go to the left and one arrow go to right. So it is both in the opposite direction. Okay, next. Okay, so because there are two types of charge and carrier, free electrons and holes in an intrinsic semiconductor, the expression for electrical conduction, which is the first equation, must be modified to include a term to account for the contribution of the whole current. So electrical conductivity is given by stress equal to N E nu E plus P E nu H. So the P is the number of holes per cubic meter and nu H is the hole mobility. Meanwhile, the UE is the electron mobility, and the N is electrons per meter cube. So for intrinsic semiconductors, every electron promotes across the band gap, leave behind a hole in the valence bands. Thus, N equal to P equal to Ni. Ni, which is the intrinsic carrier concentration. So for the finalized equation for electrical conductivity is given by sigma equal to Ni E and times by UE plus UH. Okay. Okay. To apply this equation, there is example problem 18.1 from the online textbook. So it can be seen that we need to find the intrinsic carrier concentration of the given material, which is the gallium arsenide at the room temperature. So the given info for this problem is electrical conductivity at the room temperature is 10 of power negative 6, which is for the sigma symbol. And the electron and the hole mobilities for this material, which is 0.85 and 0.04. So UE equal to 0.85 and UH equal to 0.04. Meanwhile, for the value of E is given as 1.610 times 10 power 19, as I stated before in the previous slide. So as we can see in this example problem, when we put all the info from the given problem into the equation, we get the value of the intrinsic carrier concentration Ni at room temperature of this material. Okay, that's all for my part. We give to Mustaqim to continue the presentation. Thank you.
Okay, hello. I will continue for the presentation. Okay, next is for the intrinsic semiconductor. So as we can see here, this is the graph of conductivity versus time. So the data for pure, pure silicon, which is increase with T, the concentration, and it is opposite to the metal. So based on the graph, we can conclude that the conductivity is directly proportional to the temperature, which means when the temperature is high, so it will achieve the higher conductivity. So this is because with the rising of temperature, more thermal energy is available to excite electron from the valence to the conduction bond. All right. Okay, next I will talk about intrinsic versus extrinsic conduction. So the intrinsic is a case for pure silicon. For intrinsic, the number of electrons is same with the number of hole. Means, for example, if there is 4 electron, so the number of hole also 4. Okay, next the extrinsic. So the extrinsic is the electrical behavior was determined by presence of impurities that introduce excess electron or hole. So for extrinsic, it is opposite with the intrinsic. For intrinsic, we got the same number of electron and number of hole. But for extrinsic, the number of electron does not same with the number of hole. Okay, generally there are two types of extrinsic conduction. So the first type was N-type intrinsic. So for this type, the number of electron was more than the number of hole. The impurity atom with a valence of 5 was substituted with a silicon atom. For example, like phosphorus atom. So based on the picture, the silicon atom has 4 electron. So when we substitute the silicon atom with a phosphorus atom, it get one extra electron like this here. Okay. So that's why it have a number of electron more than number of hole. For this type, there is no hole because we got an excess electron. Okay, next is the P type of extrinsic. For P type extrinsic, the number of hole more than a number of electron. The impurity atom with a valence of 3 was substituted with the silicon atom. For example, the impurity atom with a 3 valence of 3 is boron. This is a silicon atom. When we replace it with the boron, as we know, boron have 3 electron. So there will be a one hole because 4 4 substitute by 3. Okay. Hole are present in much higher concentration than electrons. Okay, extrinsic semiconductor both type N and P type are produced from material that are initially of extremely high purity. Control concentration of specific donors or acceptor are then intentionally added by using various techniques. For example, an alloying process in semiconducting material is termed as doping. In intrinsic semiconductor, large number of charge carriers are either electron or holes, depending on the impurity type that are created at room temperature by the available of thermal energy. High room temperature electrical conductivity are obtained in an extrinsic semiconductor. So next is the extrinsic semiconductors, which is the graph of conductivity versus temperature. The data for doped silicon is it is increased by doping. The reason is the imperfection sites lower the activation energy to produce mobile electron. So for T less than 100 Kelvin, it is called a freeze out state. Thermal energy insufficient to excite the electron. Okay, for temperature 150 to 550, it's called extrinsic state. And then for the temperature which is more than 450 Kelvin, it's called intrinsic state. Okay, that's all from us. Thank you.